In a distributed system, effectively routing the incoming request to the right server is very important. One common method is called hash-based routing. In this, you take something like user's IP address, hash it into a number, and then apply mod operation to get the server index where that request will be routed to. So basically, this is the formula. In this, n is the total number of servers present in your distributed system. This will make sure that the same user always reaches the same server, which is great for session consistency. Now assume we have 3 server nodes indexed as server 0, 1 and 2, and we have 5 incoming user requests with these IP addresses. Now after applying the formula, hash of IP address and mod with the number of servers, let's say this is how the final distribution looks like. In this, these 2 IPs will go to server 0, these 2 will go to server 1, and this one IP will go to server 2. This way, each user always goes to the same server, keeping their session consistent. But this setup works fine as long as the number of servers stays the same. But in real systems, we often need to scale up or down, and that's when the problem begins. Let me explain with 2 common scenarios. The first scenario is adding a new server. In this existing 3 server system, suddenly there is a huge traffic load and you need to add new server to handle more traffic. Now instead of mod 3, your formula changes to mod 4. This simple change breaks the whole mapping. Most requests are now sent to different servers. That means rehashing everything, which will cause delay and overload. Second scenario is removing a server. Now after some time, the traffic in your system is back to normal. So now you do not want to keep an extra server when it's not really needed. So in such scenarios, you scale down. In this, again, the server number changes from 4 to 3. And again, it will break the whole mapping. Most users which were mapped to new servers earlier will again should be remapped based on the reduced number of servers. That means rehashing everything again, which causes delays and overload. Here you see almost all the requests are getting redistributed, which really impacts the overall performance of your system. So how this problem of rehashing and redistribution can be fixed? We want to make sure that if a node fails, only the data that node was handling should be redistributed. Removing a node or adding a node should not impact all other nodes' data. Now this is where consistent hashing comes in. It's the smarter way to distribute keys or requests across servers, especially for the systems where number of servers changes frequently. So what exactly happens in consistent hashing? Consistent hashing uses a concept called hash ring or a circular hash space. Here the basic idea is both servers and keys are placed on a circular ring using a hash function. Each key is assigned to the next server clockwise on that ring. This way, when you add or remove a server, only a small portion of keys are affected, not all of them. Now let's see how we can actually build a hash ring. Imagine we have a 16-bit hash function. That means it can generate values from 0 to 2 raised to power 16 minus 1, which is about 65,000 possible hash values. Now we arrange these values in a circular space. Think of it like a clock that goes from 0 to 65,000 and then wraps around back to 0. This ring will be our hash space. Let's say we have 3 servers in our system, S1, S2, S3. We take each server's ID and apply the hash function to it. Suppose we got hash of S1 as 10,000. So S1 is placed at position 10,000 on the ring. And for S2, the hash comes out to be 30,000. So S2 goes to position 30,000. And similarly for S3, the hash comes out to be 50,000. So S3 is placed on a position of 50,000. Now with this, our 3 servers are spread around the hash ring. Let's say a request comes in from a user. We take their IP address and hash it. Suppose the result of that is 32,000. To find which server handles this request, we place the request at 32,000 point and go clockwise in the ring. Whichever server comes first will be the target server. In this case, 32,000 is between S2 and S3. So the request is sent to S3 because S3 is the first server that we encounter while going in clockwise direction. Let's say another request came and the hash of IP address is 12,000. It goes to S2 because S2 is the next server after 10,000. And if the hash value is 60,000, which is beyond all the server positions, we keep moving in the clockwise direction and the request goes to S1, the first server in the circle. In case the hash of IP address is equal to some server hash, then it belongs to that server only. So this is how the request mapping is done in consistent hashing. Let's understand how consistent hashing helps us minimizing the request rehashing for both the cases of adding a server and removing an existing server. Now let's say traffic load increases in our system and now we need to add a new server. So let's say we have added a new server S4 and we hash its ID that we get 40,000. Now S4 now fits between S2 and S3. Only the keys between 30,001 to up to 40,000, which were previously going to S3, are now routed to S4. So you can see only a small portion of keys are moved, which is around 10,000 keys only, and all the remaining keys are still pointing to the previous servers. Now let's see what happens when we remove a server from the ring. Suppose S2, which was at position 30,000, goes down or it is removed from the system. Now we only have S1, which is at 10,000, and S3, which is at 50,000. Now any request that used to go to S2 must now find the next available server clockwise, which is S3. So all the keys that were between 10,001 to 30,000 and going to S2 earlier, now they will go to S3. Now here also only a limited range of keys are affected. That means consistent hashing handles server removal just as smoothly as addition without having to reshuffle everything. So far it sounds like consistent hashing solves everything, right? Well, almost. There is still one issue, which is uneven distribution. Let's go back to our example with 3 servers where S1 is at 10,000, S2 at 30,000 and S3 at 50,000. Now imagine that most of the keys happen to fall in the range of either 50,000 plus or less than 10,000. That means S1 might get overloaded while S2 and S3 mostly sits idle. This happens because the servers are randomly placed and the number of server is very small. So the request distribution can become unbalanced. To fix this, we can use virtual nodes. Now instead of assigning one position per server, each server is assigned multiple positions known as virtual nodes on the hash ring. To create virtual nodes, we apply hash functions multiple times using slightly different input on the server name. We modify the server ID slightly each time before hashing it. Let me explain it with an example. If we have a server called S1, we can create 3 virtual nodes by appending the virtual node number like #1, #2, #3 to the existing server ID. So we will get hash of S1 #1 at position 10,000, hash of S1 #2 at position, let's say 25,000, and hash of S1 #3 at position of 55,000. Each of these is a virtual node for S1. And all of them still points to the same physical server of S1. We can repeat the same for S2 and S3. Now each virtual node is treated like a separate mini server on the ring, but they all actually point to the same physical server. Now instead of having 3 points on the ring, we have 9 spread out points. This will lead to better load balancing because the keys are now spread more evenly, and it will also improve the fault tolerance. If a server goes down, its virtual nodes are spread out, so other servers can take over more smoothly and all traffic will not overload a single server. So that's consistent hashing for you. A smart, scalable way to route the request in distributed system with minimum disruption when the servers are added or removed. I hope you found this explanation easy to follow and useful. In the next video, we are going to explore microservices architecture, what it is, why it has become so popular, and what kind of problems it actually solves in the modern system. So if you are curious about how large-scale applications are built using small independent services, make sure you don't miss it. Drop a comment if you have any questions or want a topic explanation in the future videos. Like, share, and turn on the notification so that you never miss out on any practical system design content. I'll see you in the next one. Till then, let's keep learning.